what was the value of, so for example, I can start with a wave function psi x, and well, when I make a measurement, the wave function collapses to a delta function, and with a certain probability I know the position of the particle is x0. I can ask a similar question that just before the prior to measurement, where was the particle? Now compare this example to an example of a room, and I have a tennis ball somewhere in the room. Well, I'll have some probability. Let's say I'm just having an x coordinate. Let's say someone assigns me a probability of finding the tennis ball somewhere in the room. It's a normalized distribution. And after the measurement, I get a delta function. I know where the tennis ball was. This is a tennis ball. So this is a classical picture, and the above was the quantum picture. And I can ask the same question. Where was the tennis ball before measurement? Notice in this case the answer was, well, the tennis ball was where it was. Measurement classically only reveals the value of the outcome, or value of the physical property like position, such as position. The question is that true even quantum mechanically? Quantum mechanically, remember, I had a wave function whose, I'm assuming it to be real, so you can just take it as a square of the wave function gives the probability density. I get a delta function after measurement. Measurement picks up some position, and the question can be same. The question can be asked in the similar way. Was the particle at x0 before measurement? And the measurement only revealed the outcome over here. So this is kind of related to the objective or subjective ignorance we were talking about, but this is a very fundamental question that so essentially what is believed in quantum mechanics is that the particle did not have a position before measurement. So in some sense, property like position was emergent as the process of measurement. And this is loosely the Copenhagen interpretation. And you can already see this is a departure from classical mechanics. In classical mechanics, systems have properties that have values, and the measurement process only reveals those values. So, well, not everyone was happy, especially Mr. Einstein, not happy with the Copenhagen school of thought and this view of nature. And they authored a paper, the Epr paper, named after the authors Einstein, Podolsky, Rosen. And essentially, the idea of the paper is it starts with a certain assumptions, what they call as the elements of reality. And they show that since quantum mechanics cannot give the elements of reality, quantum mechanics is incomplete. So there is a more final complete theory which actually tells you what these elements of reality are. So what are these elements of reality? I mean, their argument was, one has to read the paper, but their argument is that if without manipulating the system, I'm talking very loosely, in any way, if one can infer the value of a quantity or a property, value of a property, well, then that property is an element of reality. So, well, the goal of the argument, their argument is to show that quantum mechanics is not a complete physical theory by identifying elements of reality that were not included in quantum mechanics. So, we can actually go to the Einstein paper and exactly see the definition of what they described as the elements of reality. By the way, the paper is very readable, so I'll encourage you to have it, to have a look at it. So, in exact words of Einstein, Podolsky, and Rosen, for them, if this is the definition of elements of reality, if without in any way disturbing a system, we can predict with certainty uh, that is with probability equal to unity, with probability equal to unity, the value of a physical quantity then there exists an element of physical reality corresponding to this physical quantity. So the essentially the argument of EPR is rather simple. What they do is that, let's say you start with an entangled pair of qubits, and of course we have our usual guys Alice and Bob. So well, Alice performs a measurement of the spin. uh, Alice performs measurement of spin in some direction, and she measures the observable, whatever, it can be sigma x, sigma y, sigma z, but essentially it measures this observable, and let's say the result is +1. Well, a simple calculation shows that Bob will measure with certainty and get a value -1 if he measures the same observable. So you can see, if you have the quantum states, certainly if Alice is measuring sigma z, whatever outcome Alice gets, Bob is going to get the opposite. Either the state is going to collapse into this guy or it's going to collapse this guy. So if Alice is getting the result +1, Bob is going to get -1. And essentially, it's true for all directions, not only the z direction. So as soon as Alice measures and gets +1, Alice comes to know that so Alice can predict with certainty the value of the measurement of Bob's qubit. Now, Alice and Bob can be at the two corners of the universe with their respective particles and this quantum state. So, as soon as Alice measures, it knows with certainty what is the value of the measurement of Bob, which, mind you, Bob doesn't know. Uh, because for Bob, both of the outcomes are possible. So, the EPR people argued that this makes quantum mechanics at Bob's end incomplete. So Bob was using quantum mechanics, applying all the quantum theory he can, uh, and was not able to determine with certainty, which was perfectly known to Alice. And since Alice was able to recover that information without in any way disturbing Bob's particle, uh, it was an element of reality. So the inability of Bob to uh, obtain the value of the element of reality with certainty renders quantum mechanics as incomplete. So that was essentially EPR's argument, Einstein, Podolsky, and Rosen's argument. And the goal of the paper was to show that the quantum mechanics is incomplete by demonstrating quantum mechanics lacks some essential elements of reality by their criteria. Uh, well, most physicists did not buy this EPR argument. It seemed like defining what reality is, who the hell knows what reality is, defining what reality is and trying to impose on nature, this ought to be the reality. And the key experiment in invalidation, key experimental invalidation to Einstein's argument was the Bell's inequality. So, first of all, we'll come to Bell's inequality right away. The first thing to know, and I'll write it in a different uh, font, is Bell's inequality is not a result about quantum mechanics. So you can forget your quantum mechanics for the next 25 minutes, all about your knowledge of quantum mechanics. To obtain Bell's inequality, we go through a thought experiment. We'll perform a thought experiment. And we'll analyze what our notions of common sense tell us. So here's the thought experiment of Bell's inequality. Thought experiment. Alice, Bob, particle, particle. Suppose there's a third party which is preparing some particle, a pair of particles, and doesn't matter how he prepares the particles, just that he's capable of repeating the same experiment over and over again. And he sends one particle to Alice and the other particle to Bob, and Alice performs two measurements, either measurement Q having value plus minus 1 or R also having value plus minus 1. Bob performs some measurement S having the value plus minus 1, T also having the value plus minus 1. So these are essentially the physical properties P, Q, P, R, whose values are plus minus 1, and S, PS, and PT. Again, the values are plus minus 1. And let's suppose all these are objective properties. By objective properties, we mean objective properties in the classical sense. Uh, Measurement is only revealing this property. So values of Q, R, S, and T are objective. They already exist. That's the assumption. Notice there's nothing to do about quantum mechanics. We are just having some system being prepared, particle 1, particle 2, and there are these physical properties P, Q, P, R, P, S, P, T taking values Q, R, S, and T, which are objective. They already exist, and the measurement just reveals these properties. Okay, so same at Alice's end, Bob's end. Uh, so what's going on? Let's do some simple algebra and calculate the quantity Qs plus Rs plus RT minus Qt. I can simplify. These are just numbers. These are numbers. Q can either have plus or minus 1 in one experiment. R is also plus minus 1. S plus minus 1 and T plus minus 1. So I can simplify that and write it as Q plus R S plus R minus Q T. Well, because R and Q are plus minus 1, notice one of these guys has to be 0. If R is 1, Q is 1, then this is 0. If R is 1 and Q is minus 1, vice versa, this guy is 0. So in either case, it's easy to see that this equation, I can call it as 1. In either case, let me just write down the page number. It is easy to see that 1, which was Qs plus Rs plus Rt minus Qt equals to plus minus 2. Well, that's just from common sense. I assume these are the numbers, these are the values they get, and this uh, can either be plus 1 or minus, either be plus 2 or minus 2. Now, let's say the probability distribution was the following. Before the measurement, the system is in a state Q is some value Q, R is some value R. These are plus minus 1. S is S, and T is some value T. So the small Q, R, S, and T are, values which will acquire plus minus 1, plus minus 1, plus minus 1, plus minus 1. So this can depend upon how Charlie has prepared the system, so on and so forth. So what is the expectation value of these random variables? Let's say these were random variables Q, R, S, T. The expectation value of Qs plus Rs plus Rt minus Qt, well, this is the sum over all the possibilities weighted by the probability of these guys. Okay, QRST, that becomes sum weighted by the probabilities, and we already know this value was at the most 2. So this is an inequality less than 2, which is, this is a probability distribution that normalizes to 1, so 2. So we know that the expectation value of this quantity is always less than or equal to 2. Well, the expectation values can also be broken down as, since the expectation values are linear, I can also break it down as QRST, PQRST, QS plus QRST, PQRST, RS plus QRST, RT minus QRST, QT, which is nothing but the expectation values of these guys separately. Mind you, so far there is no quantum mechanics. This is just real numbers and we are just doing some algebra. Okay. Well, this result is often known as the CHSH inequality. And as usual, this is less than 2. So by repeating this experiment many times, uh, Alice and Bob can analyze their data, they can look for experiment, uh, and averaging sample over many times, they can perform and then check what's the value, whether or not this inequality is satisfied or not. So had the particles have these values Q, R, S and T before the measurement, which were plus minus 1, there's no way this inequality can be violated. There's nothing we have shown. This is just an addition using some very common sense algebra that elements of reality or the objective properties of the system will not lead to any value of this expectation value that's going to be less than, that's going to be greater than 2. Now we come to quantum mechanics. It's time to put back some quantum mechanics into the thing. Let's say I start with a Bell state. And now we are testing, does quantum mechanics violate this inequality or quantum mechanics does not violate this inequality? And that is going to give us a window, or that's going to unambiguously prove whether or not quantum observables had values of properties before measurement. So for Q, I take direction Z1 for the measurement of spin, R is X1, S is minus Z2, 2 means the second particle, minus X2, and T is z2 minus x2. I'll normalize them. Root 2, root 2. So simple calculation shows that the average QS, well, all you need to do is to put this state psi QS psi. That's what I mean by the average. That's 1 over root 2. You should try this algebra at your home. Take the state psi, RS psi was 1 over root 2. RT psi, RT psi 1 over root 2. And QT psi QT psi minus 1 over root 2. So QS plus RS plus RT minus QT, once you calculate it, this turns out to be 2 root 2. Wow. So hold on. So the quantity we were calculating yields a value greater than 2. But we thought that this value can never exceed 2. So what does that mean? Where is the paradox? So let us check the assumptions. What were the assumptions that went into the derivation of Bell's inequality? Well, there was this assumption that PQ, PR, PS, and PT have definite values Q, R, S, and T, which exist independent of the observation. Also, the assumption that Alice can perform a measurement does not influence measurements that does not influence the result of Bob's measurements. So the first assumption is called as realism, and the second is called as locality. So these two assumptions collectively are called as local realism. Well, they are certainly intuitive. I mean, make sense assumptions about how the world works, and they fit with our ordinary common sense. But quantum mechanics says that under these assumptions, there is no way the Bell's inequalities can be violated. We saw quantum mechanics indeed does violate Bell's inequality. So one of these assumptions has to give away. Either we give away the assumption of realism or we give up the assumption of locality. So most physicists are comfortable with dropping the assumption of realism, that physical properties do not have values before measurement. Values in some sense are emergent. And well, the assumption of locality means faster than speed of light travel. Alice's and Bob can be in two different corners of the universe, and Alice's outcome of measurement can indeed influence Bob's measurement in some sense. But the lesson of the Bell's inequality is that physics is not locally realistic. Either we have to give away with locality or we have to give up with realism. We cannot have both. So essentially, till now we've been doing, the entanglement was, the lesson of entanglement was, we saw quantum teleportation, superdense coding, the role of entanglement in quantum computation. We did a few quantum algorithms. The message of entanglement seems to be much deeper. And one way entanglement reveals is that physics or nature is not locally realistic. Quantum mechanics violates Bell's inequalities, hence the quantum theory is not locally realistic. So that's a deeper message in some sense of quantum information science. So with this, I think you can attempt the last problem of the latest homework set, problem 3.3, I believe. But and I've used this from Nielsen and Chong. I'm going to upload my notes as well as Nielsen and Chong uh, in the lecture. So this is from Nielsen and Chong. Okay, thank you.